Hi fellas. Okay, what we've got here is the simulation of melittin in 3 molar glucose solution. And you've got the hydrophobic groups in white, the polar groups but not charged in green, and the charged groups, that's the 4 lysines and the 2 arginines, in blue. And this is a 4 nanosecond simulation. Okay, the first thing to notice is the sugars seem to have a large propensity to stick to the surface of the peptide, rather like guanidinium. Bear in mind this is the same concentration as the 3 molar guanidinium solution. Now you have to bear in mind that the glucose is somewhat bigger than the guanidinium. In fact, it's about 3 times by mass, which of course is going to mean it moves slower. It also has a sort of fairly generic architecture to guanidinium, such that you've got both guanidinium and glucose have sort of hydrophobic faces and hydrogen bonding groups around the outside. And here, of course, you can see there's the significant propensity of the glucose to stick in a face-on fashion to the tryptophan, very similar to what we saw in guanidinium. Now you got to bear in mind that guanidinium stacks up quite happily with itself in solution. Glucose doesn't. In fact, in this case, it's more like TPA, in that TPA stacked up very well against the indole group of tryptophan, but never actually showed a face-to-face interaction like we saw with either guanidinium or with glucose. Right, now the other thing you've got to remember, of course, is the indole group has a nitrogen in the 5-membered ring, and that's actually almost that's got a charged atom type charge on it, about minus 0.7 or something. So you can see the glucose will occasionally hydrogen bond to that. However, there also seems to be a similar effect where the hydroxyl points to the center of the 6-membered aromatic ring. Again, to me this reminds me very much of the alkali metals sitting on the aromatic ring, in that the charges on the ring atoms are very small. They're only about minus 0.1 for the carbon and plus 0.1 for the hydrogen. But of course that means that it's really quite favourable, I think, to have a hydrogen bond to the centre of the aromatic ring simply on electrostatics. Okay, this is the zoom up of arginine 22, and you can see the sugars hydrogen bond quite well to this group. You can get double hydrogen bonds. Now these groups hydrogen bond much better than the lysines do. The lysines are fairly poor at hydrogen bonding to glucose. And you also see, as we did with guanidinium, there is a propensity for the glucoses to have a face-on interaction with the hydrophobic face of the guanidine motif of the arginine side chain. The protein backbone is shown as a red ribbon, and the glucoses are coloured by groups. The C-terminus is on the left. Glucose seems to have a propensity to stick to the knobbly groups of the protein. This wasn't really something that we saw with guanidinium, so glucose seems to deal much better with the uneven surface of the protein, of the peptide, whereas guanidinium was almost always a face-on interaction, carrying the waters around the edge of the molecule. residence times are long. Take for instance the blue glucose. It stays in contact with a protein for about 2 nanoseconds.